of an ideal fluid, and from there we had seen that when an ideal fluid is in static equilibrium or at rest, then the pressure gradient in it is created by gravity. So there's a vertical pressure gradient. So let's take it from that point onwards. Okay, so far what we have understood about hydrostatics, that is an ideal fluid at static equilibrium, means at rest. So if it is at rest with respect to ground frame, then there is a vertical pressure gradient of minus rho g, where rho is its density and g is acceleration due to gravity, and the horizontal pressure gradient is 0. So this is at rest in ground frame or in an inertial frame. Then we have a vertical pressure gradient of minus rho g and a horizontal pressure gradient of 0. And we had seen the derivation of this and understood that this acts because of gravity. Now let's continue this discussion further and understand another property related to this situation, that is an ideal fluid at rest in an inertial frame. So this particular property next is called Pascal's law. So Pascal's law statement is that any pressure change created in an ideal fluid is transmitted uniformly to all points inside. So let us understand the meaning of this statement with a simple example. So suppose we have a situation like this where we have a closed vessel, a closed container in which we have kept some ideal fluid like water or something at rest. So this is a sealed vessel. Now initially, let's say this has air at atmospheric pressure. So if this point is A and we have any other point inside the fluid which is at a depth of h with respect to A, and we can see that the pressure at the point A is equal to the air pressure outside, okay, and pressure at the point B is pressure at A plus rho gh, because we'll use this formula. Okay. So if we go from A to B, we can see that vertical displacement is minus h. So from this, like we'd seen last time. Now suppose next what we do is we create some pressure change by, for example, pumping out the air partially. So we keep everything else the same in the container, but we remove some of the air which is in the portion, which is in the part of the container which is above the fluid. level. So now we put an air pump here. So using this now, we have changed the pressure of the air to P equal to P naught minus delta P. Let's say. So suppose an air pump is used to pump out some air, and the new pressure, let's say P prime now, is P naught minus delta P for the air in the sealed vessel. So what will happen is that the new pressure at the point A, therefore now the new pressure at the point A will become P naught minus delta P. So you can see that at the point A, the change in pressure is minus delta P. Okay. But the new pressure at the point B will be this plus rho gh, okay, because still this formula applies, delta P by delta Y is equal to minus rho g. So the new pressure at the point B will become P naught minus delta P plus rho gh. So you can see that the new pressure at the point B is P naught plus rho gh minus delta P. So this has also become what the original pressure was minus delta P. So the change in pressure for the point B is also minus delta P. Okay. Just like this is showing us that at the point A, the change in pressure is minus delta P. So this is showing us that PA prime was what the original pressure was minus delta P. So from this we can understand that both points A and B, and like that all points, are undergoing the same difference in pressure. So all points experience a uniform pressure change because of, you know, using the air pump to remove some of the air. Whatever pressure change we have created at one point like A, that same amount of pressure change is created at all points within the fluid. It reduces by a factor of delta P, whatever that delta P is. So that is an example of the application of Archimedes of Pascal's law. Okay. So just make a note of the statement of Pascal's law and then this example. Then we'll discuss more important examples of Pascal's law application next after that.
Sir, can you scroll down?
Yeah, just a second, people. I'll scroll down. Yeah, so now having understood Pascal's law statement, let's come to the first example of the application of Pascal's law.
So 1 minute, 1 minute.
Yeah, correct. This will just make a correction here. This is PA minus delta P. Okay. So the new value of pressure at the point A is becoming the original value of pressure at the point A above, which is P naught minus delta P. So the point A experiences a change in pressure of minus delta P, and the point B also experiences the same amount of change in pressure. So any point that we compare within the fluid, the change in pressure is uniformly transmitted. That is the application of the Pascal's law principle over here. You can say that is the observation from Pascal's law. Okay, so now one of the very interesting applications of this principle or this property of fluids is in hydraulic systems. In heavy engineering, hydraulic systems becomes very
1 minute.
important part. Sorry, what happened?
1 minute, sir.
Still not finished writing?
Yes, sir.
Okay, done now.
Sir, 1 minute.
Done, sir.
Okay. So another example of application of Pascal's law. A hydraulic lift, or the more general term of hydraulic systems in heavy mechanical engineering. So we can take advantage of this property of an incompressible fluid, that pressure change is transmitted uniformly to all points. You can take advantage of that to generate a very large amount of force using a comparatively smaller amount of force. That would be done by something like this. So let's say you have two pistons like this, which are of area A1 and A2. There is some nearly ideal fluid over here. So if a force F is applied over here, it will be able to balance and lift. So if we use this force to push down this piston, it will be able to push up this piston, which is balancing a heavy load in comparison. So we can see that the pressure at this point will become equal to the pressure of this point. So without this force, assuming the piston's masses are negligible, the pressure at these 2 points will be almost equal to atmospheric pressure. If there was no mass here and there was no force applied. But having placed a mass here, the extra weight of that piston can be balanced by pressure created here, and that pressure created here can be from a comparatively smaller amount of force. You can see that by balancing the pressure at these 2 points. So by applying a force of F over here, this point's pressure increases by a factor of F by A1. And that will be enough to balance the weight of this object. The excess pressure created by the weight of the object, which is this. You can see a force equal to the ratio of these areas into mg is enough to balance and even lift that weight if we push the piston down using that force. Okay. So here A1 by A2 suppose it is a factor like 1 by n, where obviously n is a number greater than 1. So you can see that the amount of force required for that, for balancing that weight on the other side, is less than that weight. So this is the principle of hydraulic lift, that smaller amount of force can be used to generate a larger amount of force on the other side, or balance a huge amount of weight on the other side. Or this can also be used in hydraulic systems like this, where a force in a particular direction can be used to generate force in another direction. Suppose we have this kind of situation now. So you can even apply a force in a horizontal direction. On the other side, you're generating a force which is in the vertical direction like this because of that. So applied force is horizontal. The generated force is becoming vertical, and F is less than F prime because A2 is greater than A1. So it's an important aspect of mechanical engineering, hydraulic systems. You observe huge robotic systems in industrial machinery, or civil construction machinery, earth diggers, bulldozers, etc. You will see that there are those cylindrical, metallic pipe kind of structures which are used to generate large amount of force. They are hydraulic systems. So they essentially work on this principle. Obviously, it is more intricate and complicated, the machinery, but the basic working principle of hydraulic systems is this. where we have discussed about. Yeah, Tandresh, to answer your question, pressure at any 2 points which are at the same horizontal level will be the same. So pressure at a point like this, at the same horizontal level as a pressure at a point like this or like this, will be the same always.
Done.
So hope this concept is clear to all of you. Okay, let's move on next.
Sir, and sir, can you please tell it again?
Yeah, what happened?
Sir, can you please tell what is N here? I mean,
N
A.
is the ratio of the two areas.
Acha, okay,
Since
fine,
A2
fine.
is equal to N times A1, A. Understood, no?
Yes, sir. Okay, sir. Okay, sir. Thank you.
Okay, so finish writing this down.
Yes, sir. Done. Finished.
Okay. Okay, now after Pascal's law, the next thing we see, very important application, is Archimedes principle. Okay, this is the main part of hydrostatics after pressure gradient concept. So Archimedes principle, it's a very well-known statement in physics, very well-known principle, and also a very funny story of the process by which he discovered it and all that. Okay. But without getting into all that, let's understand the statement. So any body submerged in a fluid, either partially or completely, experiences an upthrust that is upward force or buoyant force, which equals to the magnitude of the weight of fluid displaced by it. So this is the statement of Archimedes principle. Okay, let's understand this in a mathematical form. So we have two situations. One where suppose a body is partially submerged in a fluid. So an example of that situation would be, let's say, we have kept a heavy object suspended using a thread or chain or whatever, such that part of it is under inside a fluid. Okay. So if part of it is inside the fluid, what we will observe here is that the tension in this rope or chain or whatever this is will actually be less than its weight, because the fluid will be applying some upward force on it, which is called buoyancy or buoyant force, where B is the upthrust or buoyant force. So this is applied by the liquid on the body. So in this case, the body is partially submerged. So according to Archimedes principle, the buoyant force will become equal to weight of fluid displaced. So that will be equal to density of the fluid multiplied by the volume of the submerged part into G. So this is the mathematical form in which Archimedes principle is stated. So here, this is the density of the fluid. This is the volume of the portion submerged. And that actually equals to the volume of fluid displaced. Because the presence of the body there displaces how much fluid? It displaces that much volume of fluid as the portion of its volume which is submerged inside the fluid. So the mass of the fluid displaced is density of the fluid into the volume displaced. And therefore the weight of fluid displaced becomes, mass into gravity, or density of fluid multiplied by the volume of fluid displaced, or the volume of the submerged part multiplied by G. So this is an example situation where we're looking at a partially submerged body. Okay. So this will experience buoyant force in this manner. Okay. We will look at a completely submerged object also in a bit, and how to apply Archimedes principle over there. Just make a note of this first. Okay, the statement of Archimedes principle, as well as the mathematical way in which it is written, that buoyant force equals to, so this is the mathematical equation of Archimedes principle. Buoyant force equals to density of fluid multiplied by the volume of the submerged part multiplied by G. Okay, so additionally, what we can understand here is that if we have a completely submerged body, of volume V, let's say, okay, completely submerged, then in that case, the buoyant force acting on it, which is density of the fluid into volume submerged into G. In that case, the volume submerged will be the total volume. Because it's completely submerged. So that's all. So this equation remains the same, but we'll have to substitute V submerged as the total volume. Okay, now the logic of this buoyancy equation can be shown very easily from, again, the pressure gradient concept. Okay, which is why I told you in the beginning that pressure gradient is the key to understanding everything about hydrostatics, whether it is the concept of buoyancy or Pascal's law or force acting on the wall of a container, all these things, everything comes from the basic fundamental principle of the pressure gradient created by gravity. So let's look at an example next. So now suppose we have a situation like this where body is suspended by a spring. Just a moment. Yeah, so body is kept suspended with part of its volume underwater. So a solid metallic block of volume, let's say 100 cubic centimeters, is kept partially submerged in water. Take the density of water to be 1 gram per cc, such that with 50% of it submerged, the spring used to suspend it which has a spring constant of, let us say, say 3 newtons per centimeter, is at an extension of x equal to, say, 2 centimeters. If g is equal to 10 meters per second square, find the upthrust on the body or on the block, whatever, the weight of the block, and from that the density of the metal. So in this, you will end up applying the principle of buoyancy or Archimedes principle, whose statement you can see is written above over here. Okay. And along with that, you will just have to solve for the equilibrium of the rigid body. It's suspended and it's at rest. So the forces acting on it should be balancing each other. So just make a free body diagram, show the balancing of forces, and in that the force of buoyancy, calculate its value using Archimedes principle statement above. The formula: density of fluid into volume of submerged part into G. So using this, you'll see you'll be able to answer all the questions. Yeah, people, let's check out the answers for this. Okay. So first of all, the buoyant force, this will be density of water in this case into volume of the submerged part into G. Now volume of the submerged part will be 50% of total volume. So it is 0.5 into 100 cc. So it's 50 cubic centimeters. Okay. So this buoyant force will become density of water. We can let it be in gram per cc. And then later multiplied with G. So 50 grams into 10 meters per second square. So that is 50 into 10 raised power minus 3 into 10 in kg meters per second square on newtons. So the buoyant force in newtons is becoming how much now? Buoyant force is becoming 0.5.
5,000. Sorry, 5 on.
0.5 is correct, right?
Yes, sir, yes.
Yes, sir.
0.5. Okay. So we don't need the free body diagram for the buoyant force. We are just given the information that 50% is submerged. So that information is necessary. This information is given, and we know the density of water is 1 gram per cc. So these are the two things we need. Okay. But when it comes to the second part, now we will make use of the free body diagram. So we will see the forces acting are the spring force, the upthrust or buoyant force, and weight. Now again, things are given to us. It's given that the spring constant is how much? 3 newtons per centimeter, right? And the extension is 2 centimeters. So kx plus buoyant force should balance the weight. So in this case, mg will come out to be 6 newtons plus 0.5, 6.5 newtons. So according to my calculation, this is the weight. Right. So this also means that the mass is 0.65 kg or 650 grams. Okay. So from that we'll get the density. That divided by 100 or 6.5 gram per cc. Right. So hope all parts of this question are clear now. So we got the mass as 650 grams and the volume of the metallic block we know is 100 cc. So therefore the density of the metal 6.5 gram per cc, or that's the same thing as 6,500 kg per meter cube. So we can also see that the relative density is 6.5. Okay, now next let's understand the derivation of the formula of buoyancy.
Sir, 1 minute, please to meet up. Yeah, thank you. 1 minute. Done, sir. Thank you, sir.
So whether we are looking at a situation where an object is completely submerged or it is partially submerged, it's easy to understand why buoyant force acting on it is given by that particular formula. So let's take this situation where it's partially submerged, this situation where it's fully submerged. So let's say this area of cross section is E, and this portion, the length of the submerged part is X. Then on this block, the force that is acting due to pressure, due to liquid pressure at the bottom here, it's let's say P into A, and the force that is acting because of atmospheric pressure here, which is P naught into A. So P is greater than P naught, and that is why the liquid applies upthrust because of that pressure difference. So the buoyant force is actually this quantity. So it is this pressure difference into the area of cross section. Of course, the force due to pressure from these sides will cancel. Horizontal components will cancel. So the net force due to pressure that is acting, that is only the upthrust. So basically, upthrust or buoyant force, it is the net force due to pressure on a submerged object. Okay, so that you can see is this one. Okay, now you can see this pressure difference will be density of the fluid into G into X. In my diagram above, you can understand this height difference from here to here is X. So you can see it is density of the fluid into A into X into G. So it is density of the fluid into volume submerged into G. Now same way in this diagram also what will happen is, the only thing is now the complete volume is submerged. So let's say the force due to pressure on this surface is P1 into area, and the force due to pressure on this surface is P2 into area. Now you can see that P1 will be equal to P2 plus density of fluid into G into L from the vertical pressure gradient concept. So here also what is happening in this diagram, the buoyant force or upthrust will be P1 into area minus P2 into area. So pressure difference into area. So that is density of fluid into GL into area. So that is also density of fluid. So it's the same thing. This equation is the same as this, but here the volume submerged will be the total volume, which is L, because it's fully submerged. Whereas this is the partially submerged case. So in this diagram, I'm not worried about other forces like gravitational force, if there's something suspending the block or not. I'm not looking at that. I'm just looking at the force because of pressure that is acting on the surface of the object. So the bottom surface of the object will always experience a larger upward force compared to the upper surface of the liquid, which is experiencing a downward force because of pressure. And that difference of the two forces is the net upthrust. And that will always be whether we have the partially submerged case or the fully submerged case. In both cases, it will always come from this formula. Is the weight of fluid displaced. Okay, so imagine any cuboidal shaped object like this, which is partially submerged or fully submerged in a liquid. So whichever be the case, partially submerged or fully submerged, the force acting on this surface will always be less than the force acting on this surface because the pressure increases with depth. F2 will be greater than F1. Okay. And that creates an upthrust or upward buoyant force. F2 is the pressure at that point into area. F1 is the pressure at this point into area. And pressure at a lower point will always be greater than pressure at another point. It doesn't matter whether the level of fluid is up to here only or it is up to here, it's completely submerged, whichever be the case. Okay, now exactly how much is the pressure difference and therefore the difference of these two forces? This is like your F1 and this is like your F2 over here, or this is like your F1, this is like your F2. So F1 and F2 are the forces on the surfaces due to pressure. So the difference between these two forces, that's what creates the upthrust. Is it clear now, Prince? So next up we have,
Sir. We have not completed it.
okay, so this is clear.
Yes, sir.
Now we move on to the application of,
Sir, just a second. Only the last line.
Sir, there you have written P2. P2 is greater than P1. That's what you have written, right? I
P2 is
mean,
greater. That's why F2
okay,
is
sir.
greater than F1 in this diagram. But that is for this one, this diagram on the side. Here 1 and 2 are reversed. Here F1 is greater than F2. Okay, this is done.
Done, sir.
Now let's look at the application of this in floating objects. So floating object is very simple. It's one which is able to balance its weight because of the buoyant force and therefore not sink. The buoyant force acting on it must be balanced by its weight. So the condition for floating is that buoyant force balances the weight. So in other words, density of the fluid into volume of the submerged part into G must be equal to mg. This is the condition for floating. So as a very simple example, a solid wooden block assume wood as a uniform density rho, floats in water, density of water being 1 gram per cc. Okay, with 0.3 fraction. Oh no, not 0.3, 0.6. So we'll make it 3/5. So with 3/5 of its volume submerged. The first thing is that calculate the density of wood from this. Okay. Second, will it float in kerosene, which has a density of 0.8 gram per cc, let's say. Okay. Okay, so just try out this question now.
So can you solve this, please?
Okay, so let's check out how many people have got the answer. Yes, Kshitij and Yash correct. Tantresh correct. Anybody else worked out the values? So you should be getting the density of wood as 0.6 gram per cc. And the answer to this, yes, it will be floating. Okay. But with, I think, 3/4 portion submerged. So in the first case, when you have water, three-fifths of its volume is submerged. So the buoyant force acting on it will be density of water into three-fifths of the volume into G. Whereas the weight of the block will be density of wood into its volume into G, because it's a solid wooden block and it's having a uniform density. Okay. So buoyancy equals to weight means density of water into the portion submerged is equal to density of wood into the total volume. So density of wood is going to become 0.6 gram per cc points using the density of water, which is given to us 1 gram per cc. Now for the second part, you can see that in kerosene oil, density of wood is still less than density of kerosene, so it will float. And again, this time it will be density of kerosene into volume of submerged part into G. So substituting these values, you can see that 0.8 times volume submerged is 0.6 times V. So the volume submerged will be 3/4 of total volume. Okay, so this is a very straightforward, simple type of question, and we should not have difficulty solving something like this at all. But remember, the calculation here is done in this way because we're talking about a solid wooden block which is having uniform density. For example, another thing that, yeah, is there some doubt?
Yeah, sir, I've done the question one in a bit different way. I got the same answer. Can I tell that method is? I just want to know whether that method is.
Yeah, tell me what method you applied, because there's only.
Sir, what I had done is, sir, I just basically used the previous formula, that is buoyant force is equals to mg, and 1 into And the buoyant force is, I mean, that I put that formula and I got the value of mass as m is equals to 3 by 5 into volume of water. So I then divided, then took water, the volume of water to LHS. So it is mass divided by volume. So 3 by 5. So it is
It's the same thing.
0.6.
No? We have done the same thing over here. Equated the buoyancy with density of water into volume submerged into G. And on the other side, equated it with the weight of. So it's basically the same thing, right?
Yeah, okay. Got it.
Okay, now one more thing we can add over here is that suppose while floating in water,
Sir,
what happened?
just a minute.
Sorry, come again?
Sir, just a minute.
Yeah, just a minute. What? But I'm
Sir, can you scroll it up? That's what he's
scroll
asking.
it up. Okay. Okay, so now while the wooden block is floating in water, if a stone is placed on it, given that the block's mass is 2 kilograms, find the maximum possible mass of a stone so that the stone does not submerge. Understood. So the wooden block is floating on water, and now you want to gently place a stone on top of it as it is floating. So it will tend to push the wooden block in, but we don't want to push it so much that the stone submerges in water. The stone should remain dry. It should not get submerged in water at all. It should not get wet. So what is the maximum possible mass of such a stone, given that the mass of the wooden block is 2 kgs? Okay, so again, I have received answers from Yash and Tantresh and Chitij, which is correct, 1.3 kg. If the others are also trying the question by the same method. So basically, if we assume that situation where we have the maximum weight just before, like if we add even a milligram of more weight, then it will tend to sink. Then the situation that we'll see will be like this, that the wooden block is just about completely submerged, but the stone on top of it is not submerged. Okay. So if we take this situation, this is the situation when the mass of the mass of the stone, let's say m prime, is maximum. So the condition for that is that the wooden block should be just about completely submerged. So now you can see that you can just take it as a combined free body diagram. So the combined weight has to be balanced by the buoyant force. Now this is equal to density of wood into its volume into G. And this is equal to density of water into the full volume into G. Okay. So now since this is given to us, the density of wood into volume is 2 kg. Therefore, we can see that the buoyant force is going to be this times mg. Okay. So it is going to be this is the buoyant force. So coming back to this, so that is the correct answer. M prime is the mass of the stone. So in the limiting condition that the stone is fully submerged, this is what happens. I mean, the wood is completely submerged and the stone is just about safe from the water. Okay,
Excuse
people,
me, sir.
so this is clear. So with this,
Sir,
we
this
complete hydrostatics.
so I have a doubt. Sir,
Yeah,
can you please explain that B is equals to what density of water into V into G
yeah.
part? I mean, after that part, can you explain? I didn't understand the part.
After that is very simple. Na? You see this quantity, the weight of the wooden block. Na? M is basically what? It's density of wood into V, and that is given to us as 2 kg.
Yes,
Okay.
sir.
Compare this quantity M with the formula for buoyant force. Na? So get the relationship between these two things. You understand? Just divide these two equations, you get this relation.
Okay, okay. All right. So
You can see that
basically, we
the
divide it.
ratio of buoyant force upon the weight is basically what it is, density of water, because it's fully submerged upon density of wood. Okay, so that's how we get this equation.
Okay, sir. Okay, sir. Got it. Got it.
So we know these two densities and we know the mass of the block. So that's how we came to know the buoyant force is 10/3g. And once we know the buoyant force is 10/3g, then we can calculate what is the weight of the stone or the mass of the stone m prime. Got it now?
Yes, sir. Yes, sir. Got it.
Okay. Okay, so with this we finish the principles of hydrostatics. Okay, you can complete HC Verma's like hydrostatics exercise. I mean, it's a mixed exercise of hydrostatics and hydrodynamics. So you can do up to question number 22 in that. Okay, in HC Verma fluid mechanics exercise, you can do up to question number 22, which is hydrostatics. Only one question in between will have a situation of oscillation. There's a spring attached to a block and the floating object is oscillating. So leave out that question because we will do that in the chapter of oscillations, which will come afterwards for us. Okay, but you can try out all these questions. You can go through the solved examples also. You can also see in your module and work out some questions from hydrostatics. Next lecture, we will discuss some of the questions and we will move on to hydrodynamics, which is the second part of fluid mechanics, which is to do with a fluid in motion. So we'll see that there's something called continuity equation and Bernoulli's equation. And from that, we calculate various relationships like the relation between pressure and speed and gravitational potential energy and all these things for a flowing liquid. So with that, we will complete fluid mechanics. So that's it for today's session, people. Thanks for attending and wish you all the best.
Bye, sir. Thank you, sir.
Bye, sir.
Bye, sir. Thank you, sir.
Sir,
Yes, Anuj, you had some doubt, but
so not related to this.
yeah, tell me what is your doubts.
Sir, in the nuclear program in any country, why can't be the same formula used for making some another nuclear bombs?
It's not the question of same formula. See, making a nuclear bomb is a very complex process. Like it involves materials, it involves the processing of those nuclear materials, it involves achieving critical mass, okay, it involves detonation. So it's not just one formula, it's an entire engineering process.
So why can't that same process be just copied and pasted? Means the same officials are working, so they know what they did for the previous
No,
one.
it's
So
highly
why
secret.
can't they?
It's not like that. It cannot be repeated like that. Huh? These are classified documentation. Like even nuclear power plants, the engineering process is highly classified. Normal people don't have access to it. It's very closely guarded secrets. Any country's nuclear program is very closely guarded secret. If and because there are leakages, that's why you have rogue nuclear powers also, no?
Hmm.
Like so many of the so-called terrorist nations and all, they have nuclear programs not from their own research. They have it because they're
Yeah, some of our neighboring countries have stolen from
yeah, see all that
the other
what
countries.
is the context of your question? Because like this goes into foreign policy, spy networks, national security, all these things. So
Yeah.
like where is the question coming from actually?
Like India has 100 and some nearly, the unofficial count is 160 nuclear bombs, and Pakistan has 5 to 6 more. So why can't we make the bombs which we have? Why can't we make some similar like them? Like why can't it be cloned?
India is making its nuclear program according to its nuclear policy. No? Like I mean, you cannot question what India's nuclear policy is. You don't have the technical know-how for that. There are scientists doing that. There are defense experts doing that. There's a budget for that. There's procurement of nuclear materials which is coming from specific places for India. You can't say that as a civilian person who's just studying physics, you can't say that, okay, why can't we do this? Why can't we do that? There are too many factors in that. That's why I'm asking, where's the question coming from?
That only that I wanted to ask. Why can't, means there might be some reason, no? But why can't we make some bombs which are similar to that?
But what? How do you know what bombs we are making and what we are not making? Before you ask a question about something, you have to have knowledge about that.
So
So
the first
what knowledge do you
test,
have of the Indian nuclear program? Because it's a very classified knowledge. What you see published in the papers and what you see like is given to the open public and all that. That is only a superficial part of the actual information. Even I don't know what the nuclear program of India is like.
so the first test was conducted, the first successful test was conducted 8 years after Homi Baba's death, or 6 years
Correct,
something,
but that is the
nearly 1972.
listen
So
to me, that
in
is the
those,
publicly declared information. You don't know what the actual information is. That's what I'm saying. And these are defense secrets. Like, what is the point of discussing this unless you are part of that nuclear program? You understand?
so it's not necessary that we have only 160. That's
Not necessary. Like that is the information that is released to the public only. Nuclear program of any country is such a sensitive defense secret, national secret that it is highly sensitive, highly classified information.
hmm,
And unless you are part of that process, you cannot understand why what decision making has gone into it. What are the constraints?
yeah.
Okay, Anuj, anything else?
Yeah. And sir,
Yeah.
in 1966, the plane by which Homi Baba was going from Mumbai to New York, that crashed on the Alps, and the remains of those the remains of that flight was never found. And later, the ex-head of CIA, Mr. Robert, he publicly on camera means he acknowledged the fact that Shastri ji and Homi Bhabha were assassinated by CIA because India was very close to make a nuclear bomb. So how can we, if the remains of those planes were never found, how can we believe that Homi Bhabha was dead? It might be that they captivated him and forced him to work for America.
See, I as a civilian have no comment about this because like, it is like beyond my information and knowledge to comment about these things. Okay. Your guess is as good as mine. It may be the case, may not be the case, we don't know.
It is he had accepted on camera. Even he has written it in his book that Lal Bahadur Shastri and Homi Bhabha were assassinated by whatever his team was, and they had made out that plan and assassinated both of them because India was very close to make a nuclear bomb. And at that time, the CIA was organizing these political assassinations in many countries where the politicians, where some local politicians or even the head of the country was trying to go against America, or their policies were against the interests of US.
The thing is, what do you want to do about it now?
I was just asking.
Like, there is no way to prove this now. Like, even if one person from CIA background has just publicly commented about it, but there is no evidence against them, they would have covered their tracks if they've done that. And obviously, like,
It has been.
there is a complex process of, there is international court and all, but unless there is some concrete proof and some evidence that you can give about this, there's nothing we can do now. So
No evidences are left behind in such assassinations or such murders by any agency.
unfortunately, nothing we can do apart from learn the lessons now, that in future you have to be able to protect your leaders and scientists.
Yeah, but who would have thought that they would kill 125 passengers just to assassinate Homi Bhabha?
Nothing, yeah. This is nothing. You just see the history of like World War II only, and you'll understand the extents to which all the major superpowers can go for military supremacy.
Yeah.
So it's nothing. This is like a very old thing. Like it's there from olden times that people in politics and power and the so-called leadership of various nations and all, they will go to any extent. There is no morality and all this in these things. So it's useless. So that is where every nation has to have its own system to protect its interests. Okay.
Yeah.
Okay, Anuj, I'll call off now because I have another lecture coming up.
Yes. Okay.
Okay. Thanks for the information. Okay.
Thank you, sir. Bye.